So in this session, we'll discuss thermal stresses in coaxially connected members subjected to temperature change delta T. So let's consider example here. This one is one copper bar. It is connected with steel bar. So this steel copper bar is fitted inside the steel bar. So we can say these two are coaxially connected members as their axis of both bars will be similar here. Now how to find stresses in this kind of members, that is in a coaxially connected members. Of course we are talking about thermal stress. So to understand this, we have to assume that the coefficient of thermal expansion of steel and copper is different. For our case, let's assume that coefficient of thermal expansion of steel is greater than coefficient of thermal expansion of copper. So what happened due to this? We know that as these bars are fixed at one end and free at another end, if you allow them to expand freely, so they will expand like this. Now for the point of time, let's assume that the steel and copper are separated, means they are not coaxially connected. If they are separate bars, so this is, let's say, steel bar, and let's say this one is a copper bar. I am assuming that separate bars having same length. So what happen? If this material of steel is allowed to expand due to temperature change, this will expand up to length equal to delta L. How much this delta L is? We know delta L is equal to alpha L into delta T. So this change in length, free expansion, depends upon coefficient of thermal expansion, and as for steel and for copper this coefficient of thermal expansion is different. So what happen? And we assume that St is greater than Cu, that is alpha St is greater than alpha Cu. Therefore this copper, when subjected to free expansion, will expand, but the length of the copper, free expansion of copper, is less than length of the steel. So delta L of St and this delta L of Cu are not same, but they are different. It is equal to alpha L delta T. Of course it is for copper, it's alpha Cu for copper, this is for steel. As steel thermal expansion is greater than Cu, so this length or free expansion is more than of the copper. Now, but this happens when they are free, they are not connected together. This bar is free, this bar is separate, and this bar is separate. But what happens if these two are connected together? So let's understand that. To understand that, we assume here again the same diagram, that is our original one. So here we assume that this is your axis and this one is, let's say, copper bar at the center, and this copper bar at the center is surrounded by a steel bar. So this one is a steel bar and at the center there is copper bar. Now as they are connected together and subjected to some temperature change delta T, here also what happen? They are subjected to expansion, also they are free here, but as they are connected together they will not expand separately, but they will expand together. Now up to what limit they will expand? If you see together, we assume that these two are hold together either by welded joint or by glue connected together. So actually it is expected that steel will expand up to here. You can see free expansion of steel is known to you. So steel is expected to expand till here and the copper is expected to expand till here, but this will not happen. And this entire system, coaxially connected bars, will not expand till here or here, but they will be in between. Means what happen? If they are free, the steel will reach up to here. So we can show like this. This is free expansion of steel up to here, and this one is free expansion of copper. But now as they are connected together, they will not reach up to here also and here also, but it will be somewhere in between. Let's assume that they will reach here. Means what happened? Expansion of steel was lesser as expected, while expansion of copper is more as expected. So we can see this one is your actual one here now. This is expansion of copper and steel. Up to here it will reach. So coaxially connected members will expand up to this limit. If you observe carefully, what happened here? The expansion of steel is reduced by this much amount. This was expected, so this is prevented expansion. While you can see here also, while copper is expanded by more amount, this is additional amount it expand. So when we try to express this in some equations, what we can write? Actually, what happened here? Why it happens? Because when it try to expand, this as they are welded together, it acts like a support and it exerts some compressive force on the steel, while it exerts some tensile force on the copper. So we can write here change in length of the copper and change in length of the steel are equal. So we can write total change in length. Total change in length of copper is equal to total change in length of Cu. Now how much change in length of the copper? How much change in length of the copper, that we can find. How we can find out? For this we know that the free expansion of the copper is alpha L delta T plus this, and for steel free expansion is this much minus this. So we can write as alpha St is greater than alpha Cu. Remember this. So for steel, okay, this is for steel. Let's say this is for steel. This is for copper. For steel, free expansion is alpha L delta T of steel. So it is up to here, but this much amount get reduced due to this compressive force. And how much it is? It is equal to PL upon E, because due to the force, when there is force acting on a bar, change in length delta L due to force P is equal to PL upon E. So due to this compressive force, this much amount reduces. This much amount reduces. So what I can write? PL upon AE. Okay. So what happened in steel? It is reduction. While in copper, free expansion is up to here. That means up to free expansion is here. So what we can write here? Delta L is equal to alpha L delta T of copper, but it added. So due to this force, there is pull force. So it will push it. Sorry, it will extend it. So we can write plus PL upon A, because there is tension in copper. You can observe here this much amount added to actual expansion. So this is PL upon A. So this formula is useful to find out stresses in a coaxially connected members when subjected to thermal stresses. It is very simple concept. What we see in here, when they are separate, expansion of steel is more while expansion of copper is less due to this assumption. But when they are combined together, they will not reach up to expected expansions. That is not as that of steel also, not as that of copper also. It will be in between, and this will act like a support. So what happen? There will be some compressive force, compressive stress acting in a steel member, while there is some tensile force acting in a copper member. And when you need to find out change in length is equal to free expansion expected minus this compression. While in copper, free expansion expected plus this tensile force. So tensile expansion due to tensile force. So here in case of copper it will be added, while in case of steel it will be reduced. Remember, of course, this PL upon AE is also for steel, and this is for copper. Now by using this formula, we can solve numericals on this concept. To solve numerical, we will use this formula. Let's solve it first. So this is numerical based on same concept. A steel bar of 30 mm diameter is enclosed in a copper tube of 30 mm ID and 40 mm OD. So case given here is a steel bar is there and it is enclosed in a copper tube of same ID and OD is 40 mm. So this is your case. So steel bar of 30 mm. Okay. So this is a steel bar of 30 mm ID and it is enclosed in a copper tube of OD 40 mm and ID same, that is 30 mm. So these dimensions are given. Along with that, temperature of composite bar is raised by 32 degrees Celsius. So change in temperature delta T is equal to 32 degrees Celsius. We can see here E of ST and E of CU are given, that is modulus of elasticity is 200 GPa. We can write 200 into 10 raised to 3 MPa for steel, while E of copper is equal to 100 GPa, that is 100 into 10 raised to 3 MPa for copper. Now you observe here alpha ST and alpha CU are given, and as per our given data, this alpha CU, which is 16 into 10 raised to minus 6 per degree Celsius, and alpha ST is equal to 10 into 10 raised to minus 6 per degree Celsius. So here you observe that alpha CU is greater than alpha ST. So this is important observation from given data. And also length of the bar is given, that is L is equal to 1.2 meter. Then find stress developed in each material. So we have to find out stress in steel and stress in copper. So this is our statement. It's very easy. We know that as alpha CU is greater than alpha ST, as per our previous concept, we know that, let's say I consider here the steel and copper. So this is your section given. We assume it is free at one end and expand due to temperature. So what happens when I suppose to heat them by temperature 32 degrees Celsius? What happens? It is expected that this assembly will reach up to here. Means if it is only steel or copper, so this one is a copper and this one is a steel. As alpha CU is greater, it will expand by larger amount, while this is steel will expand by smaller amount as alpha CU is greater than alpha ST. But as they are rigidly connected together, so when they are free, this is expansion of copper, this is expansion of steel. But as they are connected together, their expansion is not here or not here, but in between somewhere. So what happened in this case? This much expansion of copper is prevented, while this much expansion of steel is added, we can say. So this copper is subject to compressive force due to this support, and this steel is subject to tensile force, let's say of magnitude F. Now how we can write equation? As we seen, we know that change in length or total change in length of copper is equal to total change in length of steel. Now what happened here? If they are not connected together, then their free expansion is alpha L delta T. Here also it is alpha L delta T. But as they are connected together, the expansion of the copper is restricted by due to compressive force. So it is minus, how much it is? Due to force, any force F is acting, the change in length is equal to F L upon A, that is delta L, due to this force is F L upon A, therefore it is F L upon A for copper. And for steel, there is one push force, so it will try to push it, so it will subject to tension. So I am writing here P L upon A. Okay, so here it is minus, here it is plus. Now by putting this, there is F. Okay, now putting values, here if we put values, so what values are given, just that we need to put here. So alpha of copper, we know values. So alpha of copper, we are fighting for copper. Copper is 16 into 10 raised to minus 6. Copper value is alpha is 16 into 10 raised to minus 6 into length is same. How much it is? 1.2. 1.2 into 10 raised to 3 into delta T. Delta T is also same. 32 minus FL upon A. F is not known, that we need to find out. FL. L is again same, that is 1.2 into 10 raised to 3 mm. FL upon A. Area we have to find out. And diameter is given 30 mm. So diameter also we have to note down. Upon area, pi by 4 into d square, that is 30 square into E. E is how much? For copper, it is 100 into 10 raised to 3 given. Is equal to, we have to put values for steel. So for steel, alpha value is, as per given data, we can check the values here. These values are given to us. So alpha is 10 into 10 raised to minus 6. L is same, 1.2 into 10 raised to 3. Delta T is same, 32. But here it is plus this FL upon A. So how much here it is? F into L, 1.2 into 10 raised to 3 upon pi by 4 into 30 square into E. E value for steel is 200. So 200 into 10 raised to 3. If you simplify this and we take F values to one side, so taking this term here and this term here on this side, what will happen? We take F side to one side, F terms to one side, and this constant to one side. So finally we get equation 0.2304 is equal to F into 3.0315 into 10 raised to minus 5. So from this we get value of F. So F is equal to 7600.197 Newton. This is value of F. So by solving this we get value of F. Means what we consider? Total change in length of Cu is equal to total change in length of steel. In steel there is expansion, while in copper there is compression. And hence by equating these two values, unknown term is F only, we get F value. Once F is known, now we know that, let's say stress in steel. So stress in steel is equal to force upon area. Force is known to us, that is area of steel, of course, here is equal to 7600.197 upon area. Area of steel is pi by 4 into 30 square because it is solid. Okay, if we solve this, we get answer of stress in steel as 10.752 Newton per mm square. Similarly, we can find stress in copper, that is F upon ACU. F is same, 7600.197 upon area. So area of steel, copper is hollow because here it is having diameter of 40 and area of OD of 40 and ID of 30. So area of the copper is pi by 4 into 40 square minus 30 square. So by solving this, we get sigma Cu is equal to 13.824 Newton per mm square. So we find out stresses in steel and copper of these values when subjected to a thermal expansion, when heated by some temperature, and when they are welded together, or you can say glued together. So this is all about a numericals and a basic concept of coaxially connected member subjected to a thermal stress. We will continue on next topic related to thermal stress in next session.